In this video, we're going to use the first and second derivatives to analyze the geometry of this function given here, 5x cubed minus 15x. So for starters, I went ahead and plugged in the original function, the first derivative, and the second derivative into the y equals menu in my calculator, and this will help facilitate some of the calculations. You can do these things by hand as well, but it's just convenient to have it ready to go in the calculator. So in y1, I have the original function. In y2, I have the first derivative. And then in y3, I have the second derivative. So to get started, we will find the critical values. And to get that done, we're looking for values of x that make our first derivative equal to 0, and or values of x that make our first derivative does not exist. So our first derivative is the 15x squared minus 15. 15x squared minus 15. We got that using the power rule for our function. Now, if you notice, this is a polynomial. There's no division. There's no square roots. So we don't have to worry about areas or values of x where the function doesn't exist. This polynomial is defined for all values. So there is no value of x that makes our first derivative not exist. So we'll get no critical values there. We do get two critical values for the first derivative equaling 0. If you were to factor out the 15 and then factor what's left, or you could always add 15, divide both sides by 15, and then use the square root property. Either way, there's two values, x equals 1 and x equals -1, that make the first derivative equal to 0. So those are our two critical values of x that we will put on a number line in order to define the intervals of increase and decrease, as well as classify the extrema. So I'm going to put a -1 here and a +1. At this point, we can use the first derivative test or the second derivative test. They both will work. You could argue the second derivative test is a little bit easier, but I've found where a lot of students just prefer to always use the first derivative test simply because it always works. Sometimes the second derivative test will fail, and which is not such a big deal. You just defer back to the first derivative test. But if you're at all worried about knowing which one to use, you could always use the first derivative test. So the first derivative test is going to have us evaluate the first derivative on either side of each of these critical values of x. So for example, since I have these in my calculator ready, I could go to the table and I could plug in values. I could plug in, looks like I already have it here, something smaller than -1. We'll do -2. Something between -1 and 1, we'll choose 0. And then something larger than 1, we'll use +2. Now we've got our y2 is where the first derivative is located, so I'm looking at this column here, and I can see that to the left of -1, I'm getting a +45, so I know my function's increasing there. Between -1 and 1, at x equals 0, I've got a -15. That means the function is decreasing because it's negative. And then again, to the right of 1, at x equals 2, I've got a positive value, so my function's going back up. And now we can say that we've got a relative max going on at -1 because the function is increasing and then decreasing. This is going to be our relative max. And then at +1, the function decreased and then went back to increasing, so we must have a relative min there. Relative min. Now to get the outputs, we got to evaluate the original function at these two values of x. So I can go back to my menu here, and I'm interested at -1 and +1. And I can see that at -1, we have a value of +10. y1 is where the original function was. So if you plug -1 into the original, you should get a 10. That's the max. At +1, we've got a h of x equal to -10. So that's our relative min. So we've got our extrema here, one relative max, one relative min. And we can also, from this number line that we filled out, define the intervals of increase and decrease. So we'll just label that using interval notation. I've got to the left of -1, so I can label this as negative infinity, up to -1, the function is increasing. And then we'll join that with the right side of +1. These are the two intervals where the function is increasing. Again, it's increasing here, and it's increasing here. This will be positive infinity. It's decreasing between -1 and 1, so I can write that up like this. It's the interval notation referring to the interval between -1 and 1. So that takes care of perhaps even really more than the first half of this problem here. We've got the intervals of increase, decrease, and we've got the relative extreme identified and labeled. So next up, we need the inflection points and the concavity, and that's going to be a job for the second derivative. So our second derivative was 30x, h of x, h double prime of x, equals 30x. And similar to how we found the critical values, we're going to decide what values of x make my second derivative equal to 0. And then we should also consider if there's any values of x that make the second derivative not exist. Now in this case, again, the second derivative is just a polynomial. It's a line, 30x. There's no values of x that are going to make that not exist. So we don't have to worry about this. But we do have a single value of x where the second derivative equals 0, and that's x equals 0. 30 times 0 will give us 0. So the second derivative equals 0 at x equals 0, and we can call that the inflection point. So we have an inflection point at x equals 0. And if we were to plug that into the original function, we can see you get a 0 as an output. So the inflection point is 0, 0. And the only thing left to do is to define the intervals of concavity. We'll use another number line. We're going to put our value we got for x here, x equals 0. And we're going to check the left and the right of x equals 0 with the second derivative. The second derivative tells us concavity. So I could always go back to my menu here. I have the second derivative in y3. So I could plug something smaller than 0. Let's just do -1. And something bigger than 0, we'll do +1. And we can see to the left of -1, or left of 0, at -1, the second derivative is -30. So that tells me that the function is concave down. It's negative, so concave down. The second derivative is positive to the right of 0 at x equals 1, so we're concave up there. And that is the problem. We'll just go ahead and make we'll state the intervals of concavity in interval notation. So here we'll do concave up and concave down. And then interval notation, we've got concave up from 0 to positive infinity. And we've got concave down to the left of 0, so that's negative infinity. And then stop at 0. And that is the entirety of the problem. Now, we could always, especially since it's already in the calculator, we could go ahead and just hit the graph button. Maybe before we do that, actually, I'll go back to the y equals menu. I'm going to turn off y2, since that's the first derivative. We'll turn off y3. To turn this off, you just highlight the equal sign and hit enter. So the only one that's going to be graphed now is y1, which is the original function. And if I graph this, I can just take a brief look at the geometry here and make sure it matches what I got. So this looks like a max at -110. That looks good. This looks like a min at +1, -10. That looks good. 0, 0 will be right here, and it does look like a place where the function changes concavity with this concave down, and then starting at 0, back to concave up. So the results of our analysis look to match what we see with the graph. So hopefully you find that helpful, and thanks for the question. Bye.